Now we're on. Okay, Charles' Law. This is where we left off last time, right?
Yeah.
Charles' Law. Okay. Charles' Law is the temperature-volume relationship. Okay, remember we did all this last Friday when we did our matter dance. Okay. The statement. At constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. Okay, our expression for this is, oh, I need to move that. You guys already have that written there. Expression for that is V1 over T1 equals V2 over T2. Okay, or V1 over T1, it remains constant. Okay, so V1 and T1 are in the expression. That means that the moles of the gas and the pressure are held constant. They're not involved here. Okay, this does, however, imply the idea of absolute zero. It was Charles that postulated that there would be a lowest possible temperature. A lowest possible temperature that can be reached. Okay? If our volume goes all the way down, and if our temperature goes all the way down to this lowest temperature, that means our volume is going to be zero. If we keep decreasing our volume to the lowest possible amount, the only place that happens is at some zero temperature. This occurs at negative 273 Celsius, which has then been defined as 0 Kelvin. Okay. Here's how we get this. The volume divided by the temperature equals a constant. And it's V1 over T1 equals V2 over T2. So whenever we change our gas from one state where it has a volume and a temperature to another state with a volume and a temperature, okay, they're both going to equal some constant. And so that's how they stay proportional to each other. So, our example, determine the volume of a fixed quantity of gas when its initial conditions are 25 Celsius, 400 mils, its final temperature is 50 degrees Celsius, pressure is constant. Okay, so important things to see here. Initial, so these would be T1. 25 Celsius would be T1. 400 mils would be V1. Okay, so 25 Celsius is T1, 400 mils is V1. Final temperature is 50, so this is going to be T2 right here. Pressure is constant. We are looking for the volume, the final volume. So we're looking for V2, solve for V2. Are we okay getting to this spot? V2 equals V1 T2 over T1.
Yeah.
Yeah?
Yeah.
Cross multiply, divide. Okay, I think some people are going to have issues with this. So, V1 over T1 equals V2 over T2. We cross multiply. We get V1, T1, V2 equals V1, T2. In this case, we are looking for V2, so we're going to divide by T1. They'll cancel over here. V2 equals V1 T2 over T1. Okay, V1 T2 over T1. I see shaking heads. Okay, so we'll pause for a sec. Okay, question is, how do you know when it's T1, V1, or T2 or V2? In general, the initial conditions, when it says initial, those are what you're going to label as 1, and your final situation is what you're going to label as 2. Okay, and you're going to have all of them, all kinds of them, but the stuff you start with is generally labeled as 1. The stuff you finish is generally labeled as 2. Okay? Alright, here's key though. Gas law temperature calculations must be in Kelvin. So, we can't just use 50 and 25. We have to convert them to Kelvin, 25 degrees Celsius is going to be 25 plus 273 Kelvin is going to equal 298 Kelvin. Okay, 50 plus 273 is going to equal 323 Kelvin. So, V1 times T2 divided by T1 is going to show that as our temperature goes up, our volume will get bigger. We'll go from 400 to 434. You guys see that? Our temperature increased, our volume should also increase because they're proportional. Okay, which brings us to the worst name in the history of science. Gay-Lussac. Gay-Lussac. Gay-Lussac's law. He says that the pressure of a confined gas is directly proportional to its absolute temperature. Or, when the temperature goes up, the pressure goes up. Temperature goes down, pressure goes down. Alright, so the moles of the gas and what else are going to be constant?
Volume.
And the volume. So we're talking about the other stuff. When the moles of the gas and the volume of the gas are constant. Okay, that's it. Same proportions, same math stuff, but everything. So we're not really going to give an example there. It's you do it the same way. You cross multiply and divide. Then there's Avogadro's law. Yes, the same Avogadro that discovered the number of particles in a mole. This is how he did it. It was the study of gases. Okay, he says that equal volumes of any gas at the same temperature contain an equal number of particles. Okay, key point here is any gas at the same temperature and pressure contain equal number of particles. Okay, in fact, any two different gases do the same thing. If you have a mole of hydrogen gas and a mole of xenon gas, they will occupy the same volume with the same number of particles at the same temperature and pressure. It doesn't matter what the gas is. They all do the same thing. Okay, so our expression for that is N1 over V1 equals N2 over V2. Okay, how else could we write that? V1 over N2? Not quite. You can flip them over and you'll get the same expression. Okay, just flip them over, you'll get the same idea. Okay, note, 1 mole of any gas at STP has a volume of 22.4 liters. We learned this last unit. So if we have 2 moles of a gas at the same temperature and pressure, we will then have double the volume, or 44.8. Okay. All those guys bring us to Char-Boyle's law, or the combined gas law. Here's our statement for it. When a gas undergoes pressure, volume, and temperature changes, it can also produce a constant when the number of particles is fixed. And it's given by that. P1 V1 over T1 equals P2 V2 over T2. Now, it's at this point that I'm going to tell you. The only one you need to know of all these equations is this one. If you recognize that one of these is constant, it just goes away. So, let's say we get rid of, or we got this relationship here of V1T1 and V2T2. Well, that was Charles' law, right? Okay. And we have P1V1 and P2V2. That would be Boyle's law, right? Okay. So if the temperature is the same, we can just use the top half. Okay. Then if we have P1T1, P2T2, that was Gay-Lussac's law. Okay, so they're all combined into this one big equation, which is kind of funny because that's what we did on Friday. We did this on our own. So, okay, so example, determine the volume of a fixed quantity of gas at STP. Okay, what does STP mean? 0 degrees Celsius, also known as 273 Kelvin. Pressure equals 1 atmosphere. So, determine the volume of a fixed quantity of gas at STP when its initial conditions. Initial conditions are what, Caitlin? These are going to be, how would we label this one? Degrees Celsius would be T1 and P1 and V1 because they are the initial conditions. Okay. Right, and what's the final condition, by the way? This is weird and kind of funny. Read through it. Yeah. It goes to STP from these initial conditions. So this is actually going to be T2 and P2 over here. It's not always like this, but it is in this case. Okay, T2, P2, and what is V? We're looking for the volume. So, we know that. I need a smaller pen here. P1 V1 over T1 equals P2 V2 over T2. Okay, we're solving for V2, so we're going to get this. We get V2 by itself through cross multiplication. We're going to get that P1 V1 T2 over T1 P2. You don't have to memorize that. You can figure it out when you do the math. Okay. T1 equals, if this is our temperature, 40 degrees Celsius, this has to be converted to Kelvin. We've got to convert that to Kelvin. STP is 273 in 1 atmosphere. So, here we go. V2 equals P1, 1.2 atmospheres. V1, 325 milliliters. T2, 273 Kelvin. Divided by T1, which was 313 Kelvin. 40 plus 273 is the 313. P2, which was 1 atmosphere. Okay, we're going to pause here while you guys get out your calculators and figure it out. Okay, so hopefully, after all your calculations, you get that V2 equals 340 milliliters. Okay, which could kind of sound right. The temperature goes down, the pressure goes down. If the temperature and pressure go down, then the volume should go up, and that's going to be greater than our V1 there. So, okay. Next, we have Dalton's law of partial pressures. We are almost done with all this stuff. Okay. Statement. Statement. The sum. What does sum mean? Means you add them all together. The sum of the partial pressures of all the components in a gas mixture is equal to the total pressure of a gas mixture. Okay, so you may be asking yourself, what's partial pressure? I'll tell you. Partial pressure is the pressure exerted by each component of a mixture of gases. The expression is pretty straightforward. The total pressure equals the pressure coming from one gas plus the pressure coming from another gas plus the pressure coming from another gas. In other words, you can calculate all of them separately, and then the total pressure of the gas altogether adds up. All right. Okay, so, our example, determine the pressure of nitrogen in a mixture of three gases, where oxygen is 152, carbon dioxide is 8 millimeters of mercury, and the total pressure is 756. Okay, so, our total pressure is going to equal the pressure of the nitrogen, plus the pressure of the oxygen, plus the pressure of the CO2. But we're looking for the pressure of the nitrogen, so we need to get it by itself. So the pressure of the nitrogen is going to be our PT, total pressure, minus the O2 minus the CO2. That make sense?
Yeah.
You have the total pressure. Okay. You subtract from it the pressures of the gases that you know to find the gas that you don't know. Yeah? Okay. So in this case, it's going to be the 756 from the total pressure, minus the 152 from the oxygen, minus the 8 from the CO2, giving us 596. It's that straightforward. Okay? Piece of cake. Easy peasy. Even a caveman can do it.
Oh, that's not supposed to work.
Oh, Arachpode, huh? I like the caveman commercials. They're funny. Your uncle is a caveman? What? You what?
My uncle's done a couple of those for it. Like he's like the director.
Oh, okay. Okay, which brings us to, finally, the ideal gas law. All four variables can be modified. Okay, can be altered, as we've talked about them before. Pressure, volume, temperature, number of moles. They all combine into one big statement. Okay, so let's identify what an ideal gas is. An ideal gas is one that is described by the components of the KMT, kinetic molecular theory. Okay, that was one of the first things we covered in this lecture. Okay, however, real gases are what we have to deal with in real life. All gases are real gases. There are no ideal gases. The closest thing to it is helium, but that's about as close as you get. It still has some behaviors. We can actually make liquid helium at a really, really low temperature, and you shouldn't be able to make a liquid out of an ideal gas. It would just stay a gas no matter how cold you get it. Okay. No such gas exhibits ideal behavior under all conditions, but the equation can predict the behavior of real gases under most conditions. So, this is our equation. It is called PIVNERT. PV equals nRT. Remember it as PIVNERT. PIVNERT. Okay, the syllable break is the equal sign. So it's PIV equals NERT. All right. What's P? P obviously stands for pressure. Okay, in ATM. So we know these words stand for in atmospheres, volume, in liters. R is the ideal gas constant. It is the ideal gas constant for R. N is the number of moles. Ideal gas constant. And T is the temperature in Kelvin. Okay, R then equals, I'm going to erase ideal gas constant because it's getting in the way down here. So, R is this constant. It is 0.0821 atmospheres times liters over mole times Kelvin. The units are there so that they will cancel with everything when we solve our equation. Okay, I actually prefer writing this equation a different way because it shows the relationships better. And I won't mark you down if you write, if you use the equation like this. I like writing like this. R equals PV over NT. Because this is what we did last Friday. This shows all of the relationships that if your number of moles goes up with your volume and temperature staying the same, your pressure is going to go up. If you keep the pressure and temperature the same, you increase the number of moles, the volume is going to go up. Okay? N and T are not directly related. There isn't, if you put more moles in there, then the temperature is going to go down. It doesn't work like that. But take N compared to any one of the other three, or any of these two, either of these two. You'll see how it works. Temperature compared to these two guys, it works. Pressure compared to either of those two guys, it works. I prefer using this equation for it. But at the same time, I don't like fractions, and so it's easy to write PIVNERT on one line. And it's easier to remember that way. So, predictions. Using this equation, you can predict a missing variable when 3 of the 4 variables are set. So, the development of R, 1 mole of any gas of STP is 22.4 liters, or 22.4, what's our other unit for liter? Cubic decimeters. dm cubed. This is in your notes. Okay. R equals PV over NT. But if we know it's 1 mole at STP, then we know that the pressure at STP is 1 atmosphere. The volume is 22.4 liters. N is 1 mole. And T is 273 Kelvin. Okay, when you do all this, or essentially when you divide 22.4 by 273, because the ones will just leave it alone, you're going to get 0.0821. Okay, so this is how we come across the ideal gas constant. We know the molar volume at STP. Okay, our units must be in atmospheres, liters, moles, and Kelvin in order to cancel correctly with the units of R. There are other units of R for differing pressures, but I'm not going to give them to you because you guys can figure them out later. Okay, so our example. How many moles of a gas at 100 degrees Celsius does it take to fill a 1 liter flask to a pressure of 1140 millimeters of mercury? All right, if we're looking for moles, we need to solve Pivnert for N. So we're going to get N equals PV over RT, written right there. We need to convert our temperature to Kelvin. We know our volume is 1 liter, and we're looking for this pressure. So let's find our number of moles. Okay, it's already written on your page. I forgot to delete it. Okay, our pressure equals... Oh, that's right, we need to convert it to atmospheres. Aha. 1140 divided by 760 is going to give you 1.5. And then we plug everything in here. So this is going to be 1.5 atmospheres times 1 liter, 0.0821 times 373. And you multiply all that out, you're going to get 0.0494 moles. Noticing that atmospheres will cancel with the atmosphere term, the liters will cancel with the liter term, the Kelvin will cancel with the Kelvin term, leaving you with number of moles. Okay, this last part is a little tidbit, and this is not all that important, but it is something you might get some practice on a little later. Since N equals the number of moles, and we know that number of moles equals 1 molar mass of something, or the mass divided by the mass of what you've got divided by the molar mass of your substance. Okay, or grams over grams per mole. Then N really equals the mass time divided by the molar mass, or molecular weight is the other. So this can change. This N can become M over the molar mass, and this allows us to calculate the density of a gas based on STP. So this is sort of, this is extra, this is beyond the standards a bit. Okay, I may throw an extra credit question on the test with this kind of stuff. So the density of the gas is mass per volume, and this is going to allow us to calculate mass per volume of a gas. And that is it for gas laws.
Thank you for the great show.